we'll start with strings. And again, this is actually a good picture. You have a box tied here by a rope there, called string there. If we neglect the mass of it, and that string is holding that box there. Well, the reason that box is not falling down because the string is pulling up on it. Or sometimes you want to lift something up there. You have a pulley like this one. You start pulling in this direction. T here means tension. You're pulling on it. Notice this picture actually is kind of neat there. Because the box, if you look at this box has a weight. And the weight of the box will be which way? Straight down. Well, if this box is not moving, why isn't the box falling down? Because the tension in the string, that rope is actually keeping it from falling, is pulling upward on it with the value of T. And if the rope pulls with the value of T, for every action there's an equal and opposite reaction. So if this one is pushing this way, coming down like this way, if you follow that path for it, it looks like it's coming this way. It has to be canceled by another force in this direction. For every action, there's an equal and opposite reaction. And where is that T coming from? Because the person is pulling in this direction with the value of T, then the rope is pulling on that person backward with the value of T. These T's actually have to be equal to each other, because if they're not equal to each other, that rope will snap or something will move. So that's how strings actually and tensions work. So we're going to look at it. Where do we use them? You know, you see in that picture, we'll do some examples like that, but a common place sometimes in a hospital there. Somebody will break a leg. And when they break their leg, you'll see them laying in a bed. This is the foot. There we go, my art now. I forgot if I'm recording or not. Yes, I am. So this is their foot, it's a broken foot. And they take actually, they attach a plate here to the shoe, the foot there. Might be cast on it. And they take that picture and they'll pull it through a pulley there. So we'll have like a little pulley here. And we have a rope that's pulling in this direction. It might be another pulley here. And this is attached to the ceiling. Then we have another rope that goes like this. Will be a pulley here again. And we dangle some weight down. And that way it's supposed to take the pressure off the foot. When people break their neck too, paralyzed, they attach that and they pull on it so there's no pressure on their head. So you see that in the hospital all the time. And the question is, what's the mass M here? How much should I attach there to make sure something is not moving? Because if you put too much weight, it's going to pull that foot in. And if you put a little bit of weight, it's not doing anything. So you usually want to put a certain amount of weight so it will feel like there's not much pressure on your foot. So the question for this one, we have this contraption, whatever you want to call it there. Someone broke their leg. So the middle pulley here is attached to the foot. The mass M down here is actually pulling down. Find the value of the mass M. That's what we need to know. Such that the force actually on the foot, the force on the foot is 165 Newton. So find M such that the force, where is it? You have the force exerted on that foot on the sole, on this one, on that pulley there. Sole of the foot equals, 165 Newton. So let's look right here. Let's put like X and Y axes right here and look and see what we have here. Study that. The only thing I have to give you some angles here, otherwise I'm in trouble. Couldn't do the problem. And for this example, I'll make them equal to each other. They don't have to be. Makes the math a little bit easier. 40 degrees each one. So if I do a free body diagram, if I make this my y-axis right there, bless you, and this is my x-axis. If you look right here, well, we see really three forces acting on that. The question is, there's this rope pulling up in this direction, there's this rope pulling down in this direction. Are they equal to each other? Do I know? Not really. The fact the angles are the same, they will be equal, but if the angles are not the same, they won't. You know what? Let's make the angles different. I'll try to make the math easy, but let's make this angle 30 degrees. So since I have no idea, I'm going to call the tension. This cable is pulling up. I have no idea. Call it T1, tension cable 1. And call this one what? T2? Now, why isn't that pulley moving that direction? Why isn't it sliding there and just sitting under these two? What's keeping it from sliding down there? Because the foot of that person is pulling back on it. That's why it's not moving. So my free body diagram, when I do that, I see three forces acting on that. What are the three forces? Here they go. I got T1 in this direction. What angle? 30-degree angle. I got T2 in this direction. What's this angle? 40 degree. When I use negative 40, that's fine. But it's 40 degree below that x-axis. And I got the foot pulling back in this direction. And how much of that force? Well, that was given to us 165 Newton. The question is how much mass, what's M should be to get these numbers for me to work out. To give me a force of 165 here at that angle, at this angle that's attached to the ceiling. How much weight should I dangle here? The mass. Should I put 2 kilogram, 5 kilogram, 12 kilogram? What is it? Well, if I know what T2 is pulling this way, that means there's T2 pulling in that direction. I can tell you what that value is. For every action, there's an equal opposite reaction. So if this force is pushing this way, then there's one pulling up on it to cancel it. And if I know what that T2 is, I can tell you what the mass is. So my goal now is to figure out what T2 is. Now hopefully that foot is not moving. You don't want that patient, their foot is jerking and moving all the time. They'll be screaming in pain. You want to make sure that's stationary, nothing is moving. Well, if nothing is moving, that means the force is in the x direction here. The net force must be 0. And the net force in the y direction must be 0 if nothing is moving. Well, let's see. Let's take any force that's not on the x or y axis and break it down to its components. So here we go again. Another free body diagram. We're going to simplify that one that you see there. So for T1, I'm going to break it down to have two components. One in the x direction, one in the y direction. And for t, again, and for T2 is the same thing. Let's look at T1. This is T1, the top one. The fact is going up like this. That means you have to go to the right and go up. That's why one component to the right, one component up. Everyone see that, the direction of them? To go from here to here, you have to go to the right and go up. X component, Y component. Notice the angle with respect to what? To the x-axis? So the x component is what? T1 cosine 30. And the y component, T1 sine 30. Sine of 30 is 0.5. That's 0.5 T1. Cosine 30 is 0.87 T1. Let's look at T2. T2, notice to go from here to there, you have to go to the right and go down. That's why one component to the right and one component down. In this direction, the angle with respect to x again, T2 cosine the 40 degrees, T2 sine of 40. You might be saying, why didn't you put negative 40? Well, if you put negative 40, it tells you this is down. Well, I already know it's down. So I already put that. And if you put negative 40, this would be positive, so it doesn't really matter. So you could have put negative 40 instead of plus 40. Your answer is still going to be the same, but don't use a negative value here once you draw the arrow down, because the negative tells you it's pointing down. What's cosine of 40 degrees? 0.77 T2. And what's sine of 40 degrees? 0.64 T2. Now the fact that the leg is not moving, if the leg is not moving, we have what we call equilibrium, balance system. The net force in the x direction is 0, and the net force in the y direction is 0. And the net force in the y direction is also equal to 0. An easier way of saying that, because that looks like a lot of writing there, if you take all the forces pointing to the right, if you add them all in the x direction, they should equal all the forces pointing to the left. And in the y direction, y is up and down. If you take all the forces pointing upward, add them, they should equal all the forces pointing which way? Down. Well, let's see. Let's look at right here. I'll do the right side first, no reason. What is pointing up? What's pointing down? When you look at this diagram. Pointing up is what? 0.5 times T1. And what's pointing down? 0.64 times T2. That's one equation. How many unknowns in that equation? 2. Good. Let's look at the x direction. What is pointing to the right? The 0.87 times T1. What else, Alyssa? Plus To the right.
Oh, 0.87.
We have one more.
0.77.
Yep, 0.77 T2. And what do we have pointing to the left?
165 newtons.
Yep. What do you have now? You have two equations by two unknowns. I should be able to solve for T1 and T2. Notice if you solve for T1 from this equation, divide both sides by 0.5. T1 is what? 1.28 times T2. 0.64 divided by 0.5. Remember that? Solving two equations by two unknowns. Substitution method. Now you come back to this, and every time you see T1, you take it out and put that value. So 0.87, in place of T1, I'm going to write what? 1.28 times T2 plus 0.77 T2 equals 165. So 0.87 times 1.28, 1.11 T2 plus 0.77 T2 equals 165. 1.88 T2 equals 168. Can we get T2? 168 divided by 1.88, 89. If I know T2, can I now find T1? T1 is 1.28 times T2, which is 89.
Question.
Yes.
Where did you get 168 from?
Wasn't that 168 or 65? 165. From my sleep, I guess. My own numbers. I like my numbers better. 165 divided by 1.88. 88 instead of 89, okay. Let's put 88 here. So 1.28 times the 88, which is roughly 113 Newton. Notice the tension in the rope is not the same because the angles are not the same. If the angles were the same, these numbers T1 will equal T2 in this equation. Everything else stays the same. But that wasn't the question. The question here is how much weight, what's the mass here I need to put there to make sure I get the 165 pulling this way and nothing is moving. But I needed to get what T2 is to get that mass. So now let's look back at the picture. I drew that picture like this. And I said, if this is T2, for every action there's an equal and opposite reaction. In that rope, it has to be a T2 pulling in that direction. It has to be equal to that number. Because if it's not, that rope is not going to last there. If one is bigger than the other, things going to move or the rope is going to snap. Well, I don't want the rope, I don't want anything moving here, and I don't want the rope to snap. That means these two must equal to each other. So this is actually T2. So let's look at this picture here and do a free body diagram on it. We have the mass, which we're not sure what that is. We get T2 pointing upward, and now we know the value of T2. What was T2 equal to? 88. And this is not moving. Any other forces that you see there? Does anyone see any other forces? How about the weight of this? If you take a block of, I don't know, a weight, a 10-pound weight, you're in the gym and you hold it, how come it hurts? Or 10 is not going to hurt probably, but you take like a 50 pounds, you hold it, you go, it's heavy. Why? Because the weight is pulling down. And you have to hold up, keep pulling on it to make sure it doesn't fall to the ground. So is the weight pushing down, which equal to the mass times gravity. And if this is not moving, again, we don't want anything moving. If this is not moving, the reason it's not moving, because if you add all the forces pointing upward here, this should equal all the forces pointing down. We have equilibrium, balance. What is pointing upward? 88. What's pointing down? Mass times gravity, which is 9.8. What's m equal to? 88 divided by 9.8, which is 8.98 kilogram. So they have to attach almost 9 kilogram there to make sure the force on that foot is about 165 Newton and nothing is moving. I know what you're thinking. Do really nurses do all that stuff before they figure that out? No, but somebody else figured that for them. It might be a chart there that somebody went through it. For this much force, you attach that much, because they know what these contraptions are already designed. They're already made. They know what the angle. So somebody can figure that if you want 165, that's how much weight. You want 175, that's how much weight. 185, that's how much weight. So somebody had a chart. It might be attached to the door of the cabinet there. We need how much weight? You want 185? Okay, 185, it says hang 11 pounds or 11 kilograms. Boom, 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 done. But somebody had to go through that calculation for them and figure the stuff for them. Just like when you go to the dentist, they give you an injection in your mouth, going to pull a cavity out. It's based actually on your weight. But somebody did a chart for them, because they know most people are not going to sit down and calculate how much you weigh. You weigh 180 pounds. 180 pounds here says give them 4 cartridges. The cartridge is really small. Give them 4 of these. They put them in the syringe, boom, done. You weigh 200 pounds, you give them 5 of them. But there's an equation for that, and somebody figured that out. I'll do another one with strings, then I'll do springs. I'm actually covering 2 sections in one. This is called equilibrium balance. Let's see, a scenario. What we're going to give you. You have a tree here. There's your tree. Very similar to what we did. So we have a tree here. And you have your house on this end. Let's say this is grandma. Grandmas like to have birds and all the stuff. Has a chimney, rest of the house, and windows here. That's grandma's house. This is the door. You know. And grandma likes to watch birds, so she had a bird feeder. She asked you if you can do one for her. So you took a rope there, a string, a rope, whatever you want to use. You went like this, flat. But on this end, to tie it to the tree, you had to go on an angle. Like this way. This angle is 30-degree angle. So you tied one rope to the tree, put a nail there, tied a string to it. This one attached to the house, and this is your bird feeder. And this one is, I don't know, with the food in it, let's say 3 kilograms. The question is the tension in the string. What's the tension in each one? What's the tension in this one and that one? Again, the angles are different, so I know the tension is going to be different. Now, normally if you're designing these or if you're putting a bird feeder there, you want to plan for squirrels climbing there trying to steal the food. So it might be a squirrel on that. You want to make sure that string actually can hold the weight of that plus the squirrel on top of it. Because if you use a cheap string there, if the squirrel gets on top of this, that thing will snap, it's on the ground. You'll be going back and forth every day. So you have to get like a heavy rope to hold it so when a squirrel or two get on it, it's not going to break. So again, I'm going to put my X and Y axes right smack in the middle, right there. This is the X axis, that's the Y axis. So when you look at that, here's what we see. And we're hoping that this is not moving. The bird lands on it. The bird is so small, it's not going to make any damage. It's not going to make it move. You know, maybe just a hair down. We'll neglect that. So we have T1. Rama. Nope. Every time I call his name, I say, remind me of the movie, The Jungle Book. Rama. Man cub gotta go home. You got the weight down there, which is what? Mass times gravity. And what's the mass of that bird feeder? 3. And what's gravity? 9.8. Is that 29.4? And what we have here also is what? T2 at 30-degree angle. This is my free body diagram. So if you see a problem that says draw a free body diagram, that's your free body diagram. Graphing all the forces acting on that little junction right there, on that spot on the string. We can take this force and break it down to X and Y component. Any force that's not on the X or Y axis, I'm always going to break it down to its X and Y component. What do we have here? T1 unknown. We have the weight down here, which is 29.4. Now I'm going to take this one, break it down to, notice, to go from here to here. I got to go left and go up. So the X component is going to be to the left. The Y component is going to be up. You got to go left and go up. Now to the left, that's the X component, that's T2 cosine 30, which is 0.87 T2. The Y value, T2 sine 30, which is 0.5 T2. Now that bird feeder is hanging out there, it's not moving. Just sitting there. Stationary. If it's stationary, it says in the X direction, what's the net force? Both in the X direction, the Y direction, F net has to be 0. If it's not moving. The net force has to be 0. Which means what? If you take all the forces pointing in the X direction to the right, they should equal all the forces, add them all, the ones pointing to the left. And in the Y direction, all the forces pointing upward should equal all the forces pointing down. So let's look at the x direction. What is pointing to the right? T1. And what's pointing to the left? 0.87 times what? T2. That's one equation by how many unknowns? 2. We'll come back to it later. In the y direction, what is pointing upward? 0.5 T2. And what's pointing down? 29.4. What do you know? I can actually solve for T2 right there, right? What's T2 equal to? 59.2, is it? Divide by 0.5. If I know T2, can I come back and solve for T1 now? What's 0.87 times T? 59.2. 0.87 times 59.2, 51.5. So now come back here. T1 equals 51.5. So when you buy these strings, these ropes, make sure the strength on them, tensile, is actually more than 59.2, more than 51.2. Otherwise, they're going to snap them. You need to put them in. So that's how we handle strings. We use T1, T for tension. What about springs? The topic of the video was strings and springs. Well, let's talk about spring. I'm almost done with this video.
I have a question.
Yes.
So for this picture you drew,
Yes.
the goal is to find T1 and T2.
Yeah, the tension in the spring.
unknown, the two
Correct.
unknowns you have.
Correct. Because I want to know if I need to go to Home Depot or Lowe's
Right.
and buy ropes that can hold that. Imagine if you want to pick up the engine of a car. You better make sure that rope can hold way more than this, otherwise it's going to snap.
So if you gave us like tension 1 and you put the box as unknown, we could have solved.
You can do exactly. I can give you one of these. I can give you this or that,
And you can solve.
and you can solve for that. Just
As long as
applying
you
the
have
same
ang-
thing.
As long as you have 3 things. Right?
Or I can give you tension 1, tension 2, and ask you for the angle, and ask you for that. So 2 things. You can solve for 2 things actually. Yeah. Now, what about springs? Instead of strings, now let's look at springs. If you take a spring, a coil there, I don't have one with me, and you lay it flat, the spring will look like this. Right? But what's going to happen if you compress that spring? If you take that spring and you compress it now, you make it go like this. So we compressed it by this, bless you, we compressed it by this distance. We'll call that delta x or x. And if that spring, you attach something to it and you let it go, which way is going to push that object? If you compress it, that's what we did in the lab. We pushed on that ball last lab, compressed that spring, and once you fired it, which way the ball went? Backward. So when you compress it this way, the spring is really pushing which direction? In that direction. That's where the force is. So notice this one, I compressed it. I'm going to take the arrow out of this. I compressed it to the left, and actually the spring was pushing, the force was pushing to the right. What will happen if I take that string and I stretch it? I go like this. So in this case, here we go again. Oh, not this one. The original length of that was this, but now I stretched it. I pulled in that direction. And if this is free to move, what is it pulling on? Which direction? If you let this one go, is it going to go left or right? Left. So the force is going to be pointing which way? To the left. So the first thing I notice about the force in delta x is always backward in direction. If you compress it, the force wants to push it forward. If you stretch it, the force is going to be backward. And what's that force equal to? The force of a spring, it's always equal to negative. The negative, it says opposite direction to x. K times x, or delta x. What's K? K is actually spring constant. That's what K is. It's spring constant. Sometimes you have a chart with all the spring constants in it. It says if you have this spring, you get that spring. But really that doesn't work, because by playing with these springs, the value changes. Again, if you have a spring, you keep playing with it, playing with it, playing with it. It's not as stiff as it used to be. Take your car. When your car was new, when you hit a bump, you didn't feel anything. Now your car is 5, 8 years old, you hit a bump, go. What happened? You go to a bottom out. That spring from bouncing all the time, it's weak now. So how do we figure what K for the spring is? How do we figure that value? We can do that in the lab, actually. That's straightforward. How do we figure it? Here's how I'm going to figure K. Let's say I have a spring with me. I'll attach it to like a nail on the wall, and it'll be dangling like this. Nothing attached to it. It'll be dangling. This is it. There's a hook on it. Now I'll take that spring again and attach a weight to it. And it's going to, let's say this is the weight here. I put in 1 kilogram. And notice that spring gets stretched actually from here to there. That's the gap. When it wasn't stretched, when it was just normal, it was like that. It will stretch a little bit because of its weight. Now you attach that extra weight to it, it's going to stretch more. You measure that distance from here to here, and if you know that distance, you can find what K for that spring is. So I'll take my ruler and I measure that. Let's say that's 0.3 meters, 30 centimeters. So by putting 1 kilogram, we stretched it this much. Let's take this picture. Why isn't it still moving when you attach the 1 kilogram? What are the forces acting on it? Well, there are 2 forces on that, right here on that junction. We have one pulling upward, and that's the spring pulling up, and the value of that, what? K times X. The negative indicates the direction. The minus is going upward. Because you stretched it down, the force is pulling upward. So the minus sign just tells me the direction of it. And what else? We get the weight of this, 1 kilogram. The weight is mass times gravity. The mass is 1, gravity is 9.8. And if it's not moving anymore, if it's stuck there and just sitting there, that means we have balance. We have equilibrium. We have net forces of 0. So F net in the y direction, there is no x direction here, is 0. That means if you add all the forces pointing upward, they should equal to all the forces pointing down. What is pointing upward? K times X. What's pointing down is the weight. K is unknown. I'm trying to find what K for that spring is. X is 0.3 equals 9.8. Can you get what K is? 9.8 divided by 0.3. 32.7 Newton per meter. That means if you attach 32.7 Newton, that spring will stretch 1 meter long. That's what that means. So once I have K here, I can solve any problem with the spring. You tell me how much you stretched it or compressed it, I can tell you what that force is. Again, the minus sign tells me the direction of it. If you compress it like this, it's going to be a force to the right. If you stretch it like this, the force will be to the left. That's what the minus sign tells you, the direction. The value of that force is K times X. And once you have that K, you tell me how much you compressed it or how much you... That's why in the lab yesterday I said if it's hitting the ceiling, unscrew it from the bottom. What you did by unscrewing it, when you compressed it now, it used to be this much. By loosening it, you're not compressing it that much. It didn't go that high. Because we moved that piece down a little bit there. So you have less of compression, which means not going to go that high, the force. The bigger X, the larger the force. The smaller X, the smaller the force. I have one more topic, but I want to make its own video, so I'll stop here.